Hello, this is Mike and welcome back to BitFixer. Today we're on part 3 of building a new retro computer using an ESP32-S3. And today we're going to try to add audio to this using either one of these two breakout boards. This is a breakout board for a PCM5102 chip, a DAC, digital to analog converter. And this is a Max 98357A breakout board. This is an audio amplifier, and both of these use the I2S protocol, which is I2S or I2S, IIS, inter-IC sound is what that stands for, and it's a protocol for sending audio data between digital devices like this. See if we can make some sound on this thing. And let's talk about the signals that the I2S protocol uses. So bit clock is the clock for the serial input that you're providing it, and the DIN is the data input. So that's bit by bit an audio signal going into here, which will eventually be converted to analog and come out the line out jack, as you see. And the LCK is the left-right clock, which selects which channel of audio you're using. This is a stereo DAC, so you can have two channels. So let's go ahead and wire this up. I'm just going to put it up here. Okay, looks like we're hooked up here, and I just picked what I believe are three unused pins on the ESP32-S3, and the I2S driver should allow us to select the output pins. So let's go ahead and look at the code and get that set up. So we'll try to get some audio out of this. Okay, so we've wired up our PCM5102 DAC chip, and let's look at what we'll actually need in code to get that running. So fortunately in ESP-IDF we again have some examples that we can use, and in this case it's going to be I believe it's protocols. Is it peripherals? I think it's peripherals here. Yeah, peripherals, I2S, and in I2S basic we have this I2S basic standard mode example. And this is fairly bare bones. Really what it's doing is it's not presuming any particular piece of hardware you have connected up to it, but lets you specify the GPIO numbers that you want to use, so the pin numbers. And in this case it's setting up something for both reading and writing over I2S, which we will not need. We're only doing writing because we're only going to be sending audio from the S3 to the device. But we should be able to use this to get everything set up. Alright, I brought over the example code into our project here, and there's two parts to it. We first initialize the I2S interface, and then we launch a task to do the writing to the interface, where that actually writes the audio data out to this chip. So the initialize function, basically we just set up a few things to set up the I2S interface here, and then I've added in 48K sample rate, 16-bit audio, and stereo, so two channels of audio. And then I had to change the pins that were used because some of the ones I've connected to were actually occupied by the VGA interface. So 6, 7, and 8, we'll see if that works. And then we have this writing task, which essentially what's happening here is they allocate a small buffer, 2048 bytes, and then they're writing this test data into here. Now this is supposed to be an audio signal. I don't know what this is going to sound like played through the audio interface, but we'll find out. It's probably going to sound, it might be something like a triangle wave. We'll see. We'll see if we hear anything. And then this looks like, yeah, every so often it's just writing to the I2S interface, writing this buffer of bytes that we've sent repeatedly. So we'll see. Something should happen. So, I have to plug it in. That's true. Okay, it's running something. Oh, I have to turn on. Well, it's still going to output something on the monitor. Let's see if we hear anything. I hear nothing. Yeah, nothing coming from the speakers. yeah, I really don't know what this is going to sound like, if anything. So I think next thing to try, well, we should look at the clock lines and the data line on the device to make sure that we're getting something coming in there, and then let's make this into the simplest waveform we can do to get some audio is a square wave. So probably just do something where you have the maximum possible sample value followed by the minimum possible sample value repeatedly, and we should be able to hear that. There we go. Okay, so see something. Looks like it's a 1.54 megahertz signal, so something's happening in the bit clock. That sounds about right. Should be a pretty fast signal. And let's look at the digital in. And here we go. We have something happening. The signal is changing, and it can't really figure out a frequency because the signal is not consistent. But that sounds about right. It's writing different data. And what do we have here? This should be close. This should be our sample rate. And okay, yeah, it is 48.1 kilohertz. Very cool. So we have data coming through, and my guess is that this test data here is just not going to generate any audio that we can hear. So let's try a square wave. So I don't know. I just changed 4 of these to zeros, 4 of these to FFs. So maybe, perhaps that is what we're looking for. Maybe we'll hear something. Let's give it a try. Nope. Still nothing. Okay, so just looking through the data sheet here, I think perhaps this is the problem. And this is the part that caught my eye here. All formats require binary 2's complement MSB first audio data. So 2's complement is a sort of integer format where the most significant bit indicates the sign. So if it's a 1, it indicates a negative number. If it's a 0, it indicates a positive number. And here's the timing diagram. Our left-right clock, left channel, right channel. So that we saw that was 48 kilohertz, which looks about right. This bit clock is a much faster signal. That also looks good. The data, because I made the 0 and FF, if you're using 2's complement, then these values are actually right next to each other. So we have a teeny tiny square wave. So what we really want is the highest value. Well, let me work this out for a second, and then we'll try something else. Okay, so these are 4 16-bit integers. That's 8 bytes. We're stepping by 8 bytes in here. So maybe turn the volume all the way down in case this destroys our ears here. No, still hearing nothing. 24 kilohertz square wave. Maybe that's. Oh yeah, that frequency is too high. We wouldn't even be able to hear it unless you're very young. Probably. I can't hear it. Might not even be able to generate that frequency. That's like the maximum frequency you can reproduce at 48 kilohertz sample rate anyway. So let's do this instead. Turn this down, and here, quick and dirty test. We have 4 16-bit samples of minus 16,000, and then 4 16-bit samples of 16,000. So that should be a nearly maximum amplitude square wave at 12 kilohertz. Honestly, might still not be able to hear it. The ears age over time. But okay, there we go. All right, well I can hear it. Yeah. So we got something. We got a super high pitched sound. Turn that all the way down. Okay, so we have, that is an annoying sound. Alright, let's try again. It should be 6 kilohertz square wave. Okay, there you go. We're getting into the more audible range. The microphone should pick that up. Okay, so we have sound. So let's try to generate something a little more interesting. Sine wave will be useful for if you want to synthesize anything in the future. So I'll go ahead and make some edits here and be back with you in a second. A sine wave generator here. There's the sine function. The inside of this is something that I have to constantly redetermine every single time I use it, but the sine function has a period of 2 pi. You have to adjust the argument of the sine function so that you have your frequency here. I've chosen a 375 hertz sine wave, which just happens to it cleanly fits into this 2048 buffer size, so you don't have any phase shift or anything like that. Then I'm adjusting that. I multiply by my volume, and then I multiply by half of the full range of a 16-bit integer, or one less than that, just to keep it from clipping. So hopefully this should give us a sine wave at 375 hertz, and let's give it a try. So this should be a much lower frequency tone, and then should have the sound of a sine wave, not a square wave, which just means it's more of a pure tone. It doesn't have those higher harmonics. No. Oh, same problem. I didn't save this file. Nope. Nope. Didn't work. Did not work. Okay, let me look at this again. Okay, so you get bonus points if you notice that I didn't increment my sample value here, which means that it would just always be 0. So no sound. So yeah, leave a comment if you found that bug before I did. Okay. Ooh. That's interesting. It's not a sine wave, I'll tell you that much. Okay, so we've got sort of a messed up signal here. Let me try something else. Okay, I noticed something that perhaps was a problem. They had this delay in the loop here when you're writing data that was pretty long. Oh. Yeah, there we go. That sounds like a sine wave. We have this while loop where we're writing data to the I2S interface to the chip, and then they had a delay. Yeah, so they had the delay here, and it was 200 milliseconds, which is long. What you get is you were getting these little tiny bits of audio data followed by nothing, which would explain that. It should be a 375 hertz sine wave, and yeah, if you feel free to check if you want to verify that that is indeed the frequency. This is currently running on the same core as the VGA. So if you do too much work in here, it has the potential to impact the frame rate, or if it can't keep up, then you'll hear pops and gaps in the audio. So I'll just move some things around, see if we can write this data in real time. So what I'm doing here is just rewriting the sine generation code in a slightly different way. For every sample that you move forward, you have, this is the increment of your argument to the sine function. You have 2 pi times your frequency, which should be f divided by your sample rate. So every time you step forward 4 bytes in the buffer, I'm taking the sine of my current phase here. So starting at 0, then you multiply by the highest value of a signed 16-bit integer, a minus 1, just to avoid the edges, and then increment the phase by this pre-calculated increment, so we don't have to redo that every single time. That should maybe save a little bit of math in there. Okay, we get a tone. I'm going to turn that down just because it's a little difficult to listen to, but I just want to make sure that we're still, should be getting 60 frames per second on the VGA driver. Since they're running on the same core, just wanted to see if this is interfering at all. Okay, so we still hear the, okay, well, yeah, it looks like there is a problem here because we're down to 27 FPS. So we'll do a quick check. Let's do another check. Let's see if What happens if we put this on core 1 instead of core 0? Let's change that to 1. So that will compete with the emulated Z80 or the emulated 6502 that I have on here, but possibly that's less critical than interfering with the VGA frame rate. Okay, so we're back to 440 Hertz. Yeah, FPS is back to 60, and you can actually see it. It's running a lot slower. So there's a trade-off here, and I'm certain there's something that can be done. We can optimize the audio code. It's probably just using more CPU than it has to. Yeah, it's taking a long time on the screen. So yeah, definitely impacting the CPU performance. Yeah, quite a bit slower. Just a quick note from the future, by turning that sine wave function into a table lookup, so you have a sampled sine wave and you're just picking the right sample instead of doing the whole sine wave calculation, you can save a lot of time, and that way I can run the audio processing task on the same core as the VGA driver, and I got a full 60 frames per second. So that's just a quick way to speed that up. Well, now what I think I would like to do is, just for fun, we'll take our emulated PET using a 6502, and I'm just going to pick some random unused I/O addresses or unused memory addresses, and we're going to intercept those, and by writing values into those with, say, a sine wave frequency, then we'll get our audio interface to actually output that sound, so that way we can control it through, and it'll be through Commodore Basic. So I'm just going to try modifying our PET emulation so that we can read in, let's say we'll read in a 16-bit number. That will be our sine wave frequency, and then we can control it from Basic, so that'll be kind of fun. The tape buffer 1 on the PET does not appear to be used. And that starts at address 634, so I'm using the first 2 bytes of that for storing a frequency. And let's go ahead and try this out. I loaded up the PET. There's the PET emulator going again, and let's try to type this in. Hopefully I get it right the first time, since the backspace doesn't work yet. But let's see. Let's do this here. Let's see. So we're going to use the I as the high byte and the J as the low byte for the frequency. So these will just cycle through a bunch of frequencies. So let's poke out. Check the volume here. And there we go. Yeah. Oh, I hear a little pop. I don't know what that is, but yeah. So we have our oscillator that's controlled from Commodore Basic, and then ended up at the top frequency and stopped. So that's great. So that's just an example of how we could turn this off. It's just an example of how we could control capabilities on the ESP32-S3 using a virtual CPU. We can share some addresses in memory and then reserve those for special features like sound, or eventually, we can use something for Wi-Fi, and that is in fact what we use for the USB keyboard as well. There's right now we're doing it the way the PET does it, where you have a keyboard buffer and keyboard buffer length. So yeah, they're interacting through shared memory. Well, now that we have this working, I'm going to try the other I2S Breakout board I have and see how that works. This one, difference with this is a PCM5102. This is a, I'm not sure what there's the chip, Max 98357A. This is a instead of giving you a line out, which this one does, this gives you it's an amplifier for a speaker. So I do have a little 8-ohm speaker around, this one here. So I'm going to hook that up and see how that works. I'm probably going to go with the line out on the actual device in the end, just because I feel like that gives you more options, but I just want to test this out and see if that works as well. Let's try it again and see if it works with the speaker. Okay, well, I'm getting ready to unplug it. It's too loud. Oh, too bad. It's distorting. Let me try it again here. Okay, added in a 10x volume reduction. It's essentially a digital volume control where I just multiply the sample value by 0.1. Well, that's better. Yes, that sounds like the right frequency. So this one does seem to work as well. You don't get a volume control. I guess you don't get a volume control on this either. You have to do analog volume control. You could add a resistor in here, probably. Although it does say it's meant to drive 4 to 8 ohm speakers only. So that would probably kill the signal if you put an inline resistor with the audio signal there. That will about wrap it up. I'll leave you with some old school basic programming where we try out some of the audio features of the modified PET emulator on the ESP32-S3. If you liked the video, feel free to subscribe. There'll be more coming soon. Thanks for watching, and see you next time.